Okay, okay, woohoo! Okay, let's try that again. That was lame. Whoa! All right. Okay, we're going to do this, and then we're going to do counting. Okay, so I want to write a program checker. I want to check if your program is doing the right thing, right? So what is the most basic program checker that you could write is you want to check that a compiler is working, right? A compiler is just a program, right? And so you want to see if the compiler actually does what it's supposed to do, right? This is like a basic thing in computer science. When we want to write a program, you've seen this, right? You felt this, right? Remember the auto graders? What they're trying to do is check whether your program works. So in some sense, if you deliver a program to a company, they want to check whether it works. And we're going to see whether that can be done. Okay? Does it make sense? So we're going to see something very simple. Whether this compiler even terminates. Not only that it works, it produces anything that's reasonable, whether it even just terminates. Okay? It doesn't run forever. Okay? That's what we're asking. What about this problem? Can we solve this problem? And I think you guys got a preview in discussion because we had a little miscommunication on topics, but that's fine. It's good to see it ahead of time and see how it's also, it's like Shakespeare. You get to watch it be performed. Did I just compare myself to Shakespeare? Well, no, but I guess I did, but it's all tongue in cheek, right? So, but it's true. When I watch my colleagues present material, I feel like I learn it more. So it's good to see something you know. Anyway, okay. So halt. This is the real question: is I'm taking a program. I want to see if there's a program, and I'm going to name it halt. And it takes as inputs two things: a program and an input. First of all, what does it mean to take program as input, right? Okay, so it determines if P run on I halts or loops forever. That's all it does. And one thing you need to even ask this question is you need the concept of a computer. Like in the early 20th century, they didn't really have that. Okay, and you take it for granted, but it's already. This is asking a big question, right? It's a question about this computing device that we all have around us. So we need this thing. And we also have this notion of a stored program. You see, an adding machine is not a stored program. A person with an adding machine is not a stored program. This notion of a stored program is sort of integral, even in the question. Okay? And now, in particular, what it takes as an input, the program itself in this case is just a string. It's just a text string. So this program is taking as an input another program, but that program is not an abstract object, it's a text string, which describes which is a list of instructions, right? Okay, so it's very important in all of this to understand a program. You can think of it two ways. It's the thing when it executes on its inputs, but it also can be written as a text string. Okay? Okay, so that's why the text string can be an input to a program, right? I mean, this is all sort of obvious, but I just want to make it very explicit what's going on here, right? The mathematicians who developed all these incompleteness theorems and et cetera, they didn't have this notion of a program. They had to build a program out of arithmetic, build computers out of arithmetic in their papers. So they essentially designed the whole thing, designed computing in their, using arithmetic. It was actually shocking what they had to do. They had to do everything we do to build a computer, essentially. Okay, so the program can be an input to a program. Okay, so that's what it means, right? This text string program equivalence here is what we're talking about. And it sort of has to do with this self-reference I was talking about with the barber who shaves themselves, right? A program can sort of be an input to itself, right? It's kind of an odd thing. Okay? Okay, so now here's how you implement halts. So let's try to implement halt. So we could run the program P on the input I and check if it halts. That's like an easy way. I just run the program on the input I. I have a computer, I have a program, I have an input, I run it. That's fine. How long do you wait is the question. What if it runs for a while? How do you know whether it loops? You have to, when it doesn't halt, you have to state it loops forever. How do you know you're not around forever? Right? I mean, again, we have to deal with infinity, right? There's a thing with infinity here. You don't know when to decide. If it halts, it's fine. If it doesn't halt, you don't know for sure it's not going to halt later. Okay? So now so in fact, the point is you can't write this program. You can't write it. It really doesn't exist as an object. And here, let me prove it. So there is no program halt. And the proof is something like this. It says yes, no, yes. What? Oh, that's the proof. I've gone completely crazy. Yeah, okay. Is it Fermat's theorem? No. That's diagonalization. Okay, this is a cartoon of diagonalization. What I'm going to do is I'm going to make the program differ from every other program in some way. Okay, if some other program answers yes on some input, I'm going to make a program that answers no on that input. That's essentially what I'm going to do. Okay? Okay, so assume there's a program. So it's all very, very tied to the notion that program is text. Okay? So that there's a program halt. Okay? There is text that is the program halt. You can write the program, it's there, it's text, right? You can call it as a subroutine to another program as follows, right? So if halt of P on P halts, this is another program, I'm just writing it, another piece of text. If the program P, I'm going to call the program halt on the inputs P and P, and if it outputs halts, then I go into an infinite loop, right? Okay? Otherwise, I halt immediately. So in some sense, Turing answers the opposite of what halt P on P does. So whenever halt P on P says yes, Turing says no. Whenever halt on P on P says halt, Turing says no, that doesn't halt. Turing doesn't halt. Okay? So Turing does the opposite on this program P in some sense. It does the opposite of what halt does, of the program does on itself. Okay? Okay, so the only assumption here is that there's a program halt. There's no other assumption here. Right? The rest I wrote the program. We understand that's a program, and I can do that. There is text that is the program halt, meaning that the real program here for Turing is not just this 2 lines. It's this 2 lines plus the text that defines halt. Right? Okay. So there's text that is the program Turing. So this 2 lines plus the text of halt is the program Turing. Okay? And it's text. So if it's text, I can input it into itself. Right? So let's see what happens when I do that. Okay? Does Turing on Turing halt? Now we have to just see what happens when we run this program Turing. Right? Okay, so if we run Turing on Turing, does it halt? I don't know. I don't know whether it halts. Okay, let's assume it halts. If it halts, Turing on Turing halts, the first line of Turing on Turing plugs in Turing into this subroutine call, and it says halts of Turing on Turing. We know that this instruction says it halts, so therefore Turing on Turing loops forever, because line 1 says if halts on Turing says halts, then I'm going to loop forever. So this says if Turing on Turing halts, that implies that Turing on Turing loops forever. Okay? Which means it can't halt, right? So it must be that Turing on Turing loops forever. Is that correct? Okay. So let's say it loops forever, and then what happens in the first line, we call halts on Turing and Turing on the input Turing, and it does not equal halt because it loops forever. In which case, then we go to line 2 and we say it halts. So if Turing on Turing loops forever, Turing on Turing halts. So do you see a problem here? Well, okay, it's all in red. So it says if Turing halts, it loops forever. If Turing loops forever, it halts. So Turing can do neither. It can neither halt nor loop forever. Therefore, it does not. Therefore, Turing, the program, cannot exist. And now, halt does not exist, because if halt exists, I can write the program Turing. Okay, and that's a proof. Yeah. Yeah, I mean our requirements. He's saying he's asking whether it doesn't exist or it can't handle the special case. The notion of it is that it has to handle every case. Yeah, much like your 61A assignments. Right? No, I'm joking, but right? Does that make sense? Right? The notion is it has to handle every case. Right? So this is what you want from a program, to work on all the inputs as specified. It doesn't work on this input. It can't work on this input. Yeah, it doesn't exist. So do you see the diagonalization there? Okay, wait. Okay. Questions? Are there questions? Yeah. Yes. He asked, does it relate to Gödel's incompleteness? And the answer is yes. Yeah. I mean, it depends on your specification. If you ask your program to add 1 and 1, you can probably prove it works on that. Right? But this particular, I mean, some problems are doable and some problems are not. Yeah. So any program is a fixed length string. I'm going to show you this. It really doesn't look like the same proof, but it is exactly the same proof. Okay. So any program is a fixed length string, right? That's what we agree on, right? We believe that. Whatever, you have to write down your program if you're going to give it to me. And it's some fixed length string. Fixed length strings are enumerable. We can write a list of them. Okay? Program halts or not on any input, which is a string. So we could write a table. So what we're going to do is we're going to write program 1 here. And the row is, it's going to take program 1 as an input, and it either halts or it loops forever. Right? And program 2, then on program 1, you can input program 2, which is text. So you can input it, and then either, in this case, I said it halts. Program 1 on program 3, it doesn't halt. Okay. So now, do you see the diagonal? This is the diagonal. The halt program is the diagonal. Does that make sense? It just says, the halt program will tell you whether program 1 halts on program 1, and it will tell you whether the halt is the diagonal. You can determine the diagonal using the halt program, right? You can just you can say halt a P2 on P2. You can actually determine anything, but you could also determine the diagonal P2 on P2. Does it halt or not? Using the halt program, you can call it and determine the value in this diagonal. Now, Turing is exactly not halt, right? Not halt of P on P, right? So it basically just flips all these diagonals. So Turing is different from every program in this list. Turing is not in this list because say it's program 3. Well, Turing is going to loop forever. So it can't be program 3. Turing calls halt on program 3 and program 3, and then it looks at this H, and then it flips the answer, so it can't be program 3. So Turing's not anywhere on this list. The program Turing is nowhere on this list. Okay, Turing is a concept. It's a fine concept. You can have it as a concept, but it can't be a program. Right? Turing's not a program. Now, Turing can be constructed from halt. If I had halt as a program, you saw me construct it. I just write the halt program, and then I add this 3 lines. So therefore, halt cannot exist. Okay? So this is the same proof. And now you see that it's diagonalization. Okay? Yeah. Yeah, so Turing does not exist, but I can write the program Turing. That's the program Turing. Except what's missing there? We don't know halt. But now if I assume that halt does exist, then I can write Turing. Okay, so the contrapositive is that if not Turing, then not halt. If I have a program halt, that implies the program Turing. And I know not Turing, so that implies not halt. Okay, so so halt P does not exist. Why not? Programs are text. That's the big deal, right? So they can feed on themselves, right? Much like this statement is a lie. That statement is feeding on itself, right? It's referring to itself. Okay? So you could list the programs. Turing is not in the list of programs. You could argue directly. The first time I just argued directly by saying Turing of Turing neither halts nor runs forever. That's another way to argue, but it's really the same statement, and both of them are really using this notion that programs are text, and you can write them down. Okay? Both of them says there's no text which can be Turing. Okay? Okay. Yeah, so that was easy, right? This is like the central tenet of computer science is you can't solve all problems in sense, and it's like a big deal. And it's sort of, and it's a central, there are no computers back in the day, and Turing had to come up with the notion of a computing machine to actually develop this whole idea. So he, in some sense, invented computers. And stored programs in his concept of a Turing machine. Also, these incompleteness theorems, in essence, Gödel, what he did is he arithmetized computing. He said, this is program 1, this is program 2, this is program 3, using arithmetic and various simple statements to sort of arithmetize all these statements. And he arithmetized all logical statements because they're text. And so in some sense, we're getting off cheap, right? Because we didn't have to do the whole building of the computer, right? That's why it's one slide. Really, what we're relying on is ASCII. Does anybody even know what ASCII is? Anybody know what ASCII? Yeah. Okay. There's this encoding of text, right, and programs. So, that's what we're doing. Okay. Okay, there's other undecidable. Now that programs are text, you can now decide other things are hard, not just halt. Okay? So does a program P print hello world? I think this was in your discussion, but just to review it, for those who went to discussion. How? Okay, what is P? I'm going to say this over and over again. What is a program P? Well, it's a program, but it's also text, right? That's key. So we can look at the program P, okay? We can look at a program P. So when we want to solve the halt P of I. Say I want a program that does this, and I want to use a subroutine, a program that tells me whether a program hits a hello world program. Okay, so what I'm going to do is make P prime as follows. What I'm going to do is I'm going to look at the text in P. It's text. So I could look at all the exit points, right? Whatever language, there's some way you exit, right? The bottom of main, like in C, the bottom of main, or even in Python, I think, the bottom of main, the bottom of the main file. If you go off the bottom, that's when the program exits, right? Or you can look and search for exits anywhere. And now for each one of those, you can, right before it exits, say print hello world. Right? First you remove all the print statements, and then you find all the exit points and you add this statement, print hello world. And right before it exits, what is the program going to do? What's it going to do? Print hello world, right? So this program, this new P prime, if P exits, P prime will print hello world. Moreover, if P prime prints hello world, the only place I'm printing at all is at the exit points. Okay? So therefore, if P prime prints hello world, that means the program P halted. Okay? So call prints hello world. So now if I want to answer the question to this, whether this halts on this input, I just have to see whether P prime halts on that input. Okay? It's sort of both the trivial and the sublime together, right? Because here's the stupidest thing ever. I just look at all the exit statements and print hello world, right? Nothing. Okay, but now we see that, oh, well, that just means even determining whether a program prints hello world is impossible in general, right? So it's sort of interesting, right? P halts if and only if P prime prints hello world. So many things one can ask about programs are undecidable in this way. Do you exit this statement? Do you ever execute this statement? That could be undecidable, right? Because you can just make a statement that captures exit. Okay? So all of these sort of general questions about programs and their behavior are all, not all, but many, many of them are undecidable. Okay? And it's sort of a shocking thing. And this way of translating from one undecidability result to another undecidable result is we don't have to redo the diagonalization. We can just sort of say we could solve the halting problem using this subroutine for this other program. And that's what we do. Okay? But, there's other things. Can a set of notched tiles tile the infinite plane? So the way they prove this is, again, they designed a computer using a set of notched tiles. And once they do that, and then the question is whether it goes forever or not, is the same question of whether you halt or not. Okay? Does a set of integer equations have a solution? Here's an example. Does this have a solution? This problem is undecidable, right? If you have a general set of integer equations like this, you can actually then again construct a set of equations that allow you to simulate a computer. Okay? Okay. Now, one has to be careful. Is there an integer solution to this equation? That's not undecidable. Okay? The answer is either yes or no. Either there's a solution or there isn't. That's not what undecidable means. Undecidable means, given any equation, can I decide whether it has integer solution or not? Can I have a program that decides for any equation, any set of equations? And in that statement, there's this notion of infinity, right? Because any set of equations means I have to deal with an arbitrarily large set of equations. And already then once you have that, you have an infinite set of things, inputs, that you have to deal with. Okay? This problem is not undecidable. This is not the problem we're talking about. We're talking about, for any set of Diophantine set of equations, no program can take any set of equations and always correctly output whether or not there's an integer solution. Okay? So in computer science, we're not obsessed about this one equation. We're obsessed about writing programs that will solve all equations of this form. Okay? So, yeah, they're interesting things. It's like math and formal systems. They can't, and you see the connection. These undecidability and completeness theorems are very connected to this undecidability here. The computer programs can't completely, we can't completely understand ourselves. That's what it's saying, right? There's some sort of inconsistency in that. Okay. No program can tell if any other this is an example of a problem of not completely understanding computer programs, right? And it's diagonalization. So the program takes an input. You assume there's this program halt. Diagonal or Turing loops if P halts and halts if P loops, right? So what does Turing do on Turing? It doesn't loop or halt. So therefore, it doesn't exist. And halt doesn't exist. So this is just the same proof again. Okay? Okay, so this is, it's one thing that it was deeply connected to math and logic. It's even true at the next level in terms of complexity. Computation is sort of a lens for how things work. This notion that we want to see how things work in the world, and Turing, in addition to doing this computability stuff, also tried to understand linear systems, inventing condition number, because condition number is something you think of when you think about computing the answers in these for these systems. That makes those things converge. He also, there's a puzzle for there's this fly, and there's all of us, right? We start as a cell, but we all have eyes and ears and fingers. How did the cell know to start building those? What chemical process broke the symmetry there? At first there's a cell, and then there's another cell, looks exactly like the previous cell, and so on. So he studied this process for this kind of fly, where the body, it builds the body, and then eventually it makes stripes. So he tried to figure out how the chemicals interact to start encode, to compute, if you will, a way to draw these stripes. So he made a model for this. They're still studying these models to this day. And there's people are doing all of this now, and researchers are doing this here. Professor Vazirani works on quantum computing. There's models for evolution. They're all really now intricately connected to computing. So this sort of thing as a paradigm is out there. Okay, your future. What's your future? I don't know what your future is. In this course, it's probability. I presume you'll have a great future. But a bag, so let's just talk about probability here. Okay, so I have these marbles. This bag contains these marbles. What's the chance that if I take a random ball from this bag, it'll be blue? Yeah, now we can count, okay? It's 3 out of 8, right? You count the number of blues, and then you count the total, and you divide. So we get to divide again. So forget the no divide and multiplicative inverses. We're going to divide now. Okay, you get to divide again. So you should be happy, or not, or you have to divide again. Okay? But in probability we divide a lot. Okay? So we take the number of blue balls over the rest of them. So to get started, we're gonna talk about counting. Okay? How do you count objects? Okay? Okay, so probability Professor Ayasevar will teach it. It's Bob Back. For years I called him Babak, and then he told me when we started teaching together he's Babak. So I was like, okay. And I think that's probably not right either. If you're from Iran, I'm sorry. I'm not sorry for you. I'm sorry that I'm. Okay. I'm sorry that I'm butchering the pronunciation. Okay, so I have this thing. My name's Satish. What? Satish. What? Satish. Satish. Satish? Yeah, that's good. And then I say, that's why my kid's name's Sam. Yeah, so, yeah. It's an algorithm, actually. That's an algorithm. So the algorithm is the following, right? So what happens is this thing, it's all awkward. Everybody's awkward. I don't really care. But they feel bad. So I want to make everybody feel better. So I tell this joke. So it's when you're out there, you can do algorithms with computers, but you should also see how the world works, right? And try to optimize, right? I'm just trying to make everybody feel comfortable, right? But my kid really is named Sam. So... And Alex and Renee, but okay. So yeah, we're going to do some stuff. Okay, so let's look at some stuff. Okay, how many outcomes are possible for K coin tosses? How many poker hands are there? How many handshakes are there? Different possible handshakes are there between n people? How many diagonals in a convex polygon? How many 10-digit numbers? How many 10-digit numbers without repetition? Right. Okay, so we're going to sort of attack all these problems. So let's start with the simple one, is how many 3-bit strings? So how many different sequences of 3 bits? Okay, they're 3 bits. And a bit means it can be 0 or 1. Okay? Okay, so the way you do this is the first way you do it. It's called the first rule of counting. The way you do it is you see how to write them all down in an organized fashion. Okay, that's what you do. Okay, you see how would I write down a sequence of bits where I make that sequence. I'm going to make that sequence, right? And clearly the way you do it is you write down the first bit, then you write down the second bit, and then you write down this third bit. There's no mystery here in how you write down a 3-bit sequence, right? And now, when you write down the first bit, you have 2 choices, right? So you have 2 choices, 0 and 1. And now, for the next bit, say you wrote down a 0. For the next bit, you could write down a 0 or 1. And if you wrote down a 0 again, you could write down a 0 and 1. And here, too, you could also do that. And here, you can sort of flesh this all out. And you can see, oh, what is this? How many final bit sequences do I have? Well, it's all the ways I can make choices in this tree. Okay? So now, how many choices could I make here? It's 2, right? And then how many choices can I make here and here? There are 2. And how many choices could I make in all of these 4 places? There's 2. So the total number is 2 times 2 times 2, right? So it's fairly straight. 1 leaf for each string. Okay? So there's 8 3-bit strings. Okay? So this is the first rule of counting, right? If you make all the separate possibilities, if you could write down all the separate possibilities in a fashion where you make a sequence of n1 choices, then a sequence of n2 choices, then a sequence of n3 choices, all the way up to nk, and at the end, once you've made all these choices, you get an element of the set you're counting, and you can generate all the elements of the set you're counting, then you just multiply them together. It's this tree. Okay? So it's the same argument, right? So you have n1 choices here, and you have n2 choices here, and n3 choices here, and so on, right? So the number of these leaves, the number of leaves below here is n2 times the number of leaves below this one, because there's n2 of these. Okay? And so a little induction gives you that the total number of leaves in this tree is the product of the n sub i's. Okay? So in this picture, it's 2 times 2 times 3, right? There's 3. The degree here is 3. Okay? Any questions? Okay, so I have to be a little careful with the exclamation points here. I have a tendency to use exclamation points, but unfortunately mean something. So, how many outcomes possible for K coin toss? Now, with this first rule, we could already answer a bunch of these questions. 2 ways for our first choice, 2 ways for the second choice, and so on. So you get 2 times 2 times 2. And what will that be? How many 2's are there? It's K coin tosses, so it's 2 to the K. Okay? How many 10-digit numbers? How many 10-digit numbers are there? Well, there's 10 ways for the first choice, 10 ways for the second choice, and so on. So 10 times 10 times 10, 10 to the K. Okay? Does that make sense? It's fairly straightforward. I mean, there's a little glitch here, but I'll get to the glitch here in a minute. How many n-digit base m numbers are there if we're taking base m? Okay, so now you just have to get m and n in the right place. So why don't you do that yourself, and then I'll show you. It's either m to the n or n to the m. Which one is it? Yeah. Okay, there's m ways for the first one, m ways for the second, and so on. It's m to the n. Okay? Now, is 09 a 2-digit number? That's one of the questions. Usually people stop me after this first one. But is 09 a 2-digit number? Yeah, so depending on whether you think that's a 2-digit number or not, you can change this counting to m-1, where you're not allowed to have 0 in the first place. And the same counting rule works, right? Because now you're saying the number of choices for the first digit is all m but 0. You can't have 0 in the first digit. Does that make sense? So you can say I'm counting these objects. Oh, those aren't the objects I'm counting. I want something different, you can maybe change the counting procedure to count the different thing. Okay? How many functions F map S to T? Right? Now the knees knock a little bit because there's some math in here. There's functions and sets in S and T. But it's not so bad. What is a function from S to T? Well, it's a value for the first element of S1. It's a value for the second element of S1, the third element. So now how many possible values are there for this function on S1? Well, it could be any value in T. So it's the size of T. So there's T ways to choose the value for f of S1. There's the size of T ways to choose the value for f of S2, and so on. So you get the size of T to the size of S. Okay. How many polynomials of degree D modulo P? What about that? Okay. So we have coefficients. Let's think about the coefficient. What's a polynomial of degree D? Okay, so I'm going to review a little bit. What's a polynomial? You can specify it in one way. You could just specify it with the D plus 1 coefficients, right? So P ways to choose the first coefficient of x to the D, P ways to choose x to the D minus 1, and so on. And there's D plus 1 coefficients. So it's P times P times P. So it's P to the D plus 1. Yeah. Okay? Okay, good. So now, but there's another way to do this. Is there another way to represent polynomials? Yes. Yeah, you should all say yes, right? Isn't there another way to represent polynomials besides the set of coefficients? There's lots of other ways, right? Okay? We just pick D plus 1 x values, and then we need to pick y values, right? D plus 1 points determine a polynomial. So for an arbitrary x value, what you do is you pick a value for it at that x value, you pick a value for it at the second point, and so on. And how many points do you have? You have D plus 1, and look, it says there's P to the D plus 1 polynomials. Okay? So I counted it in two different ways, and I got the same number. Right? So that's good. So it gives me some confidence that this point representation is real, right? I better have gotten the same number of polynomials, of distinct polynomials. Right? If I didn't get the same number, then everything we did last week was wrong. Or I made a mistake in counting it here. One of the two. Right? Okay. Any questions? Okay. Okay, so you can also count permutations. How many 10-digit numbers are there without 10 digits? 10 digits, that's the number of numbers are there without repeating a digit. Okay, so the first digit can be anything. The second digit can be anything. Can't be the first digit, right? And so on. So it's 10 times 9 times 8 all the way down to 1, so it's 10 factorial. Here I'm allowing myself to have 0 first. It becomes more complicated if 0 is first otherwise. Okay? In this case. Okay, does that make sense? How many different samples of size k from numbers without replacement? So now we're going to pick from n numbers. We have 1 through n, say, and I'm going to pick a number from them. And now I've gotten that number. This is what we do when we select students. Yeah. No, I said it, in this case, it can be 0, yeah. I mean, it's more complicated to count it without 0. Right? Yeah. It would be, I don't think it's that complicated. It's just 9 times 9 times 8 times 7 times 6. If you just can't pick 0. And the second digit can't pick the first digit, so then the rest will be working. Okay, let's count it 0. Say you don't want a leading 0. How many ways are there to pick the first number if you can't pick 0? Well, there's only 9 possibilities, so you'd say 9. Now, for the second one, you can pick anything you want other than the first number, so it's still 9. So it's not more complicated. I was wrong. It's just 9 times 8, 9. It's not much more complicated. So how many different samples of size k from n numbers without replacement? So this is what we do, right? We pick a subset of the population, as that's what this is asking. How many different ways are there to pick a subset of the population where we care who we pick first and second and third? So there's n ways for the first choice, n minus ways for the second choice, n minus 1 ways for the second choice, and so on. So you get this expression. You just have k terms. There's k terms because you're multiplying. You have k choices again, and it's slightly odd. It's slightly not visually not good because you have this +1 there, but that's just what you have for k terms. Another way to write it is n factorial over n minus k factorial. Okay? It just factors out everything below. How many orderings of n objects are there? And that's n ways for the first one, all the way down to 1, which is n factorial. Okay? So this is just this one counting rule gets you a long way. For many of these objects, this one counting rule actually gets you pretty far along the way of counting those kinds of objects. Okay? How many one-to-one functions from S to S are there? Okay, these are bijections now. How many of them are there? Did we see this already? We already counted these in a sense. They are permutations in a sense. This is a permutation, right? It's a permutation of your elements, right? There's a size of S choices for f of S1, S minus 1 choices for f of S2, and so on. So the total number is the size of S factorial. Okay? So a one-to-one function is a permutation. It's sort of a permutation of the elements if they're the same domain and range. So what it says is multiplying by a mod p gives you a permutation of the elements. Okay, it's a way to permute the elements. Okay. Let me give you a break. I'll give you a break. Okay, so let's count some more stuff here. So let's count poker hands. Okay, so here just to get people oriented, a poker deck contains 52 cards. Okay, and a poker hand has 5 cards in it. for those who don't play poker. Okay, so it's 5 cards is a number of cards in your hand, and there's 52 cards in the deck. So we already know if we want to describe a poker hand, you can describe the first card in it, and there's 52 possibilities for the first card, and and then after you've taken that card is no longer in the deck. So there's 51 possibilities for the second, and so on. And you're picking 5 of them, and it looks like that. Now, is that correct? Is that what you think of as a poker hand? Are these the same poker hand? Right, they're the same poker hand. We think of them as the same poker hand, right? So in some sense, do you think that's the right expression for counting the number of poker hands, or is it different than that? It's probably different, right? Okay, so the second rule of counting is, in this case, the difference is just the ordering, right? Here, the fact is, if you just took all your poker hands and if you took your hand and you ordered it in some canonical order, say from lowest to highest, and clubs to hearts or clubs to spades or something, I don't know. So you can order the cards, and if you order them, you would obviously order this. I don't know. Either way, this is 2 of the extremal orders. But if the order doesn't matter, right? Then you have to get rid of this notion of ordering. Okay? You have to take it out. So what we do is, if the order doesn't matter, we count the ordered objects where we think the order does matter. And for today, let's just call the poker deal. It's a poker deal, right? When you get a poker deal, you get your first card, and you get your second card, and you get your third card, you get your fourth card, and you get your fifth card. So those are the ordered objects, right? Because you care which one you got first. Okay, but when you actually look at the object, the thing that you're interested about it is you just care which subset you got of poker hands. So you have to take out this ordering. Okay? So the number of orderings for a poker hand, how many orderings are there for 5 cards? Well, it means factorial. That's just me. When I tend to have the exclamation mark, but now it's not good to use the exclamation because it means factorial here. Okay? So the total number of orderings here is 50. Why is it 5 factorial? The total number of orderings is just the permutations of the cards. Right? So there's 5 ways to pick the first one, 4 ways to pick the second one, 3 ways to pick the third one, 2 for the fourth, and 1 for the last. Okay? So this is the expression you get at the end. I mean, the funny thing is, you know what? Is that even an integer? Yeah, it's an integer because it's the number of poker hands. And the number of poker hands has to be an integer. I don't know. Right? Does that make sense? Yeah. Well, how many cards are in the poker hand? Yeah, that's why to 48. Yeah. Because there's 5 terms there. I think you're used to seeing it a different way, and we'll see that different way, and I'll come back to you and give you a shout out. Okay. Oh, this way. Here you go. Now I can give you a shout out. Shout out. Okay, so, right, this is what you're used to seeing. Right, so what happens is these 5 terms come from 52 factorial over 47 factorial. You get rid of all of them. Okay, so I mean, in some sense, what I said was fairly generic. It just says how many ways are there to pick 5 items out of a set of size 52. Right? How many ways to choose 5 items out of 52 possibilities? All right. So this is, if order doesn't matter, you count the ordered objects and then divide by the number of orderings. And so this is, I don't know, I made this diagram. I think it may be helpful, but let me tell you what we're doing. I want to count the number of blue objects, but you can't count them because that's too easy. Okay? So instead we're going to count the number of red objects. And how many of them are there? How many red objects are there? 9. Okay. Now for each blue object, how many red objects are pointing to it? 3. So how many blue objects are there? Is it 9 divided by 3? Does that make sense? Okay. How many red nodes are 9? How many red nodes are mapped to any one blue node? That's 3. So how many blue nodes? Well, it's 9 over 3. That's all we're doing. Right? So we count the number of unordered objects, and those are the red things. And then we say, well, for each blue thing, that corresponds to 3 red things. And so therefore, I can just divide to get the size of the blue things. Okay? So how many poker deals? That's how many deals are there? These are ordered objects, or the red objects. There's 52 times 51 down to 48. How many poker deals per hand? Map each deal to an ordered deal, right? So there's 5 factorial ways to do that, right? So each one of these deals, the ordered deal is just one of the, just say you put them in order, and you say all the ones out of order are all the permutations, which are 5 factorial. So how many poker hands? It's the same process. Okay? Is there questions? No. Okay. Okay. So choose 2 out of n. So here, the unordered objects is, let's say I choose the first one of my out of n objects. I have n choices, and I choose the second one, which is n minus 1. Okay, so now it doesn't matter whether, say, I chose 1 and then I chose 2. It's the same as choosing 2 and then 1. Okay, so say I chose A and then B. It's the same object as B, choosing B and then A. Okay, so you divide out by 2 factorial, which is 2. Right, all the ways to arrange the set you chose. Okay, which is also this expression. Choose 3 out of n. It's the same thing. You multiply n times n minus 1 times n minus 2. That's the number of ways to choose them where order matters. Here, A, B, C, B, C, A. All those would be different in the top, and those would be those red objects. And then we say, well, there's 3 factorial ways to permute A, B, C. So there's going to be, for each set A, B, C, there's 3 factorial ways to permute it. So to get a deal, so we divide out. Okay. This is the same for n choose k. This expression here, the n factorial over n minus k factorial, leaves k terms. N times n minus 1, n times n minus 2, k times. Right? It gets rid of all the others. And then you multiply by k factorial. So this notation is n choose k. And you may have seen it in, does this seem familiar to you? Did you see, maybe in high school they would use C, a big C with an N and a K, a prescript and a postscript, right? It's the same notation. I've never seen that other than in high school math books. That's the other notation. This is what we use. Okay? Okay, so here it is. You have this thing. It's the first rule. The poker hands. That's the delta. That's the degree in the graph. So this notion here, I'm just using a 3-card poker deal. So here are all the deals. Q, A. These are all the red objects, right? The blue objects are the unordered objects, which ironically I'm just sorting. My representation is sorted because I don't care which order it is, so I just pick a representative which is sorted, which is queen, king, ace. And then I say all the other sortings are the red objects. Okay? So the degree of this graph would be 6, unlike what's illustrated, but it's the first rule. Okay? So and that's the proof. And that's the second rule. You divide. Okay? So choose k out of n is the ordered set is n factorial over n minus k factorial, and the orderings of one hand is k factorial, and you divide. So that's a proof for k out of n. Okay? Okay, here's an example. Okay, what's the number of orderings of anagram? Okay, so the total different ways this is what you did in high school, I believe. So anagram, how many letters, how many orderings of anagram are there? Well, here, the ordered set, where you care about the A's, you think of the A's as different. It's 7 factorial, right? Is it 7? Yeah, 7 factorial. So that's the first rule. But the A's are the same. You really can't tell the difference, right? So you have to deal with this. So anagram is really, you have to think of anagram as, what we counted are the red objects, these unordered things. We thought of the A's as different. There's A1, A2, and A3. Okay? When we counted 7 factorial, we're looking at all of these letters as different. So there were 7 ways to pick the first one, and then 6 ways to pick the second one, and 5 ways to pick the third one, and 4, and so on. Okay? And so these are the red objects. These are the ordered objects. So we're saying that A1, A2, or A3 are all different. Okay? So there's lots of different ways that. Now this is one ordering, one of the blue objects, which is one ordering of the things where you can't tell the difference between the A's. So all these different patterns here, this one and this one, both correspond to this one. Because these different A's here really don't look different here, right? So they're the same. So how many of these red objects are there? Well, there's all the ways to permute these A's in that position, which is 3 factorial, right? I could put A1 first, or A2 first, or A3 first, and then I could pick 2 in the second in the position of the second A, and so on. 1. So it's 3 factorial. So here the number of orderings of anagram is 7 factorial over 3 factorial. It's the second rule. How many orderings of a letter? That's easy. Everybody should be able. How many orderings of this letter is there? 3 ways to choose the first, 2 ways to choose the second, 1 to choose the third. Okay, how many orderings of the letters anagram? Ordered, except for A. It's mostly A, right? The G, it matters whether the G and the R are in different orders, right? So the total ordering of 7 letters. Total extra counts of ordering of the 3 A's is 3 factorial. So 7 factorial over 3 factorial. This seems familiar. Okay, that was a joke, but okay. How many orderings of Mississippi? We did it on the last slide. That was a joke. It's always great when you have to explain your humor. How many orderings of Mississippi? Okay, so now it's going to be a little bit more complicated, right? Okay, the ordered objects, there's 11 letters in total. There's 4 S's, 4 I's, and 2 P's. And there's 1 M, I guess. So there's 11 factorial where you think of each S as different. All the S's and all the P's and all the I's are different. If you thought of them as different, it would be 11 factorial ordered objects. Okay? Now for each ordered object, you have, for the S's, now we're going to use the first rule of counting again. We're going to try to find all the number of orderings that correspond to all the different orderings of the letters S, the different kinds of S's, and make them into 1. Okay? So now this first one is for S's. So we say, well, let me just think about the S's. My choice of designing all these orderings is I'm going to build all the orderings. And I'm going to build all the orderings by first taking all the orderings of the S's. Okay? And that gives me a bunch of possibilities. There's a bunch of possible orderings of the S's. And then my next set of choices is to say all the possible orderings of I's. Okay, so I'm making all the possible orderings of the S's, the I's, and the P's in an order. I'm going to first take all the possible orderings of the S's, and then I'm going to multiply by my second choice will be all the possible orderings of the I's, and then multiply by all the possible orderings of the P's. Okay? This way of counting the number of ordered objects per unordered objects is again using the first rule of counting. Okay? So it's just one time. You can go fast. I could just blow this by, but everywhere I'm only using two ideas, right? Here I'm doing the divide. That's what I'm showing you here. But even when I count the number of orderings, I'm counting again, and I'm counting using the first rule of counting by looking at each of these things separately as choices. All the possible orderings of the S's, all the possible orderings of the I's, times all the possible orderings of the P's. Okay? And those are the number of orderings of these letters if they were distinguishable. Okay. Okay, so now I want to show you a couple of other things. Actually, it seems to be... okay, so there's two indistinguishable jokers in a 54-card hand. So how many 5-card poker hands are there out of this deck? Okay? So... is it 54 choose 5? It isn't, because there's these two jokers that look the same. Okay? So if you have one of the jokers or the other joker, they both look the same to you. So they're not different. Does that make sense? That's what's going on here. Okay. So one rule is you can sum over disjoint sets. Now, there's numbers here, okay? There's a lot of numbers here, but you have to think about what we're doing. We're counting the objects, a set of objects. And the set of objects here are the poker hands, okay? Now I'm going to split this set of objects, these poker hands, into two sets, into different sets, and those sets should not overlap, okay? That's what I'm going to try to do. Sum over disjoint sets. So one disjoint set is I could just think of one subset of my set of poker hands is just if I have no jokers in my poker hand, right? That's easy. I know how many there are there because there's 52 cards that aren't jokers, and I'm choosing 5 of them. And we have this nice notation for choosing 5 out of 52, right? The number of ways to choose 5 out of 52. So that's for no jokers. Then if you have one joker, you have a joker in your hand. So how many other cards do you have in your hand? 4. Okay? And what are you choosing them? They can't be a joker. The other 4 cards can't be a joker, so what are you choosing from? 52 cards. So you're only making 4 choices. 52 times 4. 52 choose 4. Okay? And now, if you have 2 jokers in your hand, you just pick you put those 2 jokers in your hand, and now you have to pick 3 more. And now there's 52 choose 3 ways to choose that 3 more. Okay? There's one way to choose both jokers. Okay? Okay, so now we could also have done this with 2 distinguishable jokers in 54-card deck, right? And let's say we say, how many 5-card poker hands where the jokers are distinguishable? Okay, well, we could do the same thing. We could use a sum rule. We can say, what if the hand had no jokers? It's 52 choose 5. Okay? And now we're going to count the number of cards. And first of all, let me argue, these are disjoint sets, right? Any poker hand with no jokers is clearly not going to be in the set of poker hands with 1 joker because it has no jokers. And the set of poker hands with 1 joker is clearly not going to be in the set of poker hands with no jokers because it has 1 joker. So they're disjoint. Okay. So now this one. Okay, so now for the next one, I'm going to try to describe or build a hand with 1 joker. And so what I have to do is I have to pick a joker. How many jokers are there? They're distinguishable this time. I can tell the difference. So it matters. It's a red joker and a black joker, okay? So then there's 2 possibilities. So it's 2 choices. Again, I'm using the first rule. There's 2 choices for which joker, right? That's the choice I'm making. I'm making 2 choices here. I'm choosing 4 cards, and I'm multiplying by the fact that I could choose 2 jokers. Okay? And then finally, for 1 joker, for 2 jokers, there's only one way to pick both jokers. You pick them both. Okay, so it's 1 times 52, choose 3. Okay? Okay, wait a minute. This was stupid, right? Is there an easier way to do this? To choose a 5-card poker hand out of 54 distinguishable cards? What is it? Does everybody see an easier way to do this? It's choosing 5 cards from 54. We even have notation for that, right? 54, choose 5. Okay. And now I proved a theorem, right? You see I proved a theorem? What's so funny? It's just too entertaining to know. You're dying out there. Okay, so okay, but it's my okay. This is true. All right, we proved this theorem. You see, we proved this theorem. Like, who knew? Like, I guess we could do some algebra and verify it, but we don't need to verify it because we proved it, right? Pretty nice, I think, actually. Who knew those expressions were the same? Who cared? But who knew? Okay. So that's sort of a. We can do an algebraic proof of this, but do we really want to? Right? So it's sort of an interesting thing. Yeah. Why would you want to do a proof of that? This is supposed to be plaintive. Let's do the algebraic proof. No. Okay. So. We're going to get into this sort of exercise again. But we counted things in 2 different ways. And you remember way back in graph theory, I said the same thing. Like somehow it's very useful to count 2 things in 2 different ways, right? Twice the sum of the degrees was equal to twice the number of edges, right? And then we can set those formulas to be equal, those expressions to be equal to each other. Those are theorems, okay? Okay, so now we have the sum rule for a disjoint set of sets, the union of those sets. That's what we're doing here. This is the union, right? We're saying the set of jokers, the set of cards with no joker, union with the set of cards with 1 joker, union with the set of cards with 2 jokers. Okay, so that's what we counted using the sum rule. And now what we can say is, what we can talk about is. So just use reasoning for all subsets. So we didn't do that. Okay. I changed the order here. Okay, so let's go on. Let's talk about this other rule. Okay? For any set S and U, now we're going to count the union of the set. And we're going to say it's the size of S plus the size of T. Before, we had no intersection, so the size of the intersection was 0. So it was just the size of S plus the size of T. But here, in general, we could actually do this for any pair of sets. Okay? So what we're saying is the following. We're trying to count the size of the union, which is this whole thing, everything in both circles. Right? So these are the guys in T, and we know how many there are. Right? That's the size of T. Okay? And we know how many elements are in S, and that's the size of S. Right? And then, do you see, if we add them up, what have we done? If we add up these numbers, what have we done? Do we get the size of the 2 sets together, or have we done something wrong here? These elements here in the middle, they're both in T. So when we added up, when we wrote the size of T, we're kind of counting all the elements in this green space, all of them, including the ones in this red spot. Okay? So if we write down the size of T, what we really did is count all the elements in this green spot, in this green circle. When we wrote down the size of S, we counted all the elements in the blue circle. So that means the guys in here were counted twice. Right? So what should we do to deal with that? We subtract, right? Right? What we have now is when we add the size of T plus the size of S, we have the size of the whole thing plus these elements, we've counted them twice. So we have to subtract them off, so we only count them once. Okay? So this is inclusion, exclusion. So what you've done is you've included all the elements from all the sets, and then you realize you counted them twice, so you subtract. Okay? Okay. Okay, so this is the rule. So how many 10-digit phone numbers have 7 as their first or second digit? That's what we want to say. Okay? So S is a set of phone numbers with 7 as the first digit, and the size of S is equal to 10 to the 9th, right? Why is it equal to 10 to the 9th? Yeah, there's 10 slots. There's one choice for the first one, and then 10 choices for the other 9 slots. So that's 10 to the 9th. What about the phone numbers with 7 as a second digit? It's also 10 to the 9th, right? Okay. And now, what is the intersection? You see, this a priori, this seems hard because you can't, when you add these things, what could happen? If you can't just add these sets because somebody could have a 7 in their first digit and in their second digit, right? So these sets overlap in this way, right? S intersect T is the phone numbers with 7 as the first and the second digit. Okay? Okay, so the S intersect T is equal to 10 to the 8th. So the answer is this is the answer. So you add up S plus T plus you subtract the things in common. Okay? Okay, so for counting, the first rule is you make an object out of a sequence of choices, where if ni is the number of choices for choice I, the number of objects is you just take the product. Okay? The second rule is when order doesn't matter, you just divide out the orderings. If you can divide out all the different orderings. First, you figure out how to count the ordered objects, and now for each object, you look at all the possible orderings that shouldn't matter, and you divide out by that. And the Mississippi is like a really good example because the way to count the orderings in Mississippi sort of uses the first rule of counting like 3 or 4 times. Okay? And now the sum rule, the size of a union of disjoint sets is the sum of the sizes. And inclusion-exclusion is the size of the union of sets, is the sum of the two sets. It's much more complicated with more sets. The size of the union of sets is the sum of the sizes minus the size of the intersection. Okay? Oh, okay, good. So we're done early today. So we'll see you.